Hello and welcome back. We're here at Hackers on Planet Earth, Hope 2020. The talk and conference, everything's going fantastic so far. Thanks for being part of it. Up next is Anya Petroska. Anya, welcome.
Hello, everyone.
It's great to have you here. According to the bio online, you did your PhD in Anonymous Communication Systems at University College London and worked a lot in the Tor area, Mixmaster, these technologies. Today's talk is about resistance to the NSA level global adversaries in the NIM MixNet. And what we're going to do is play a video for about 20 minutes, and then we'll come back with Anya with questions and answers. If you're in the live chat, you can put your questions there and we'll get to them a little later. Let's roll that video.
Hello, everyone. Thank you for joining my talk. Before introducing the NIM MixNet, let's first look into why do we need it in the first place. Every time we send a message, visit a website, make an online purchase, or any other online activity, we leave a digital trace, the so-called network metadata. And as it turns out, this metadata, which is simply a set of all unique characteristics associated with our online communication, reveals a lot of significant information about us. Even if we reach out for privacy-enhancing technologies, like, for example, end-to-end encryption, we only protect the content of our communication, but not the metadata. Similarly, if we use private coins, like Zcash or Monero, such coins protect only our privacy on-chain, but do not prevent metadata leakage. So, in result, the network adversary can easily trace with whom are we communicating, how often, when, and so on and so on. So in response to the danger of tracking the metadata of the internet communication, services like VPN became popular. VPN simply builds an encrypted tunnel between a client and the VPN server, which acts as a proxy that forwards the client's communication into the web. This allows the users to hide their IP location and hence bypass, for example, censorship and geolocation blocks. However, although VPNs offer enhanced internet privacy and protection against data hacking, they have several weaknesses due to their centralized nature. First of all, the VPN provider acts as a trusted proxy and hence knows about all of the website an individual is accessing. So we're not anonymous vis-a-vis the VPN provider. And the VPN providers might keep the logs of our activities, although officially they promise not to, in order to share them with third parties. Secondly, even if the VPN provider will behave honestly, users can be still de-anonymized by powerful network eavesdroppers who can simply track the routed network traffic based on the size and the timing of the data packets, and hence easily correlate our IP address with the services we're visiting. In contrast to a single proxy VPN, Tor builds upon a decentralized network of nodes run by volunteers. Tor forwards traffic via multi-hop connections, and each connected user opens a long-lived circuit, which is a path built of 3 hops, the entry guard, the middle relay, and the exit relay. And all of the user's communication is now routed via this predetermined circuit in fixed-size cells. Each data packet sent via the circuit is layer encrypted by the sender, and each relay, upon receiving a packet, removes a single layer of this encryption. Such onion encryption ensures that none of the relays has visibility on both the source of the traffic and the final destination, nor, of course, the content. So, without any doubt, Tor is a much better solution for anonymous communication than VPNs. However, Tor still doesn't make our traffic fully anonymous. The Tor relays forward the received packets in a first-in, first-out order. This means that an adversary watching traffic in the Tor network could perform an end-to-end correlation attack by watching packets entering and leaving the network and performing timing correlation to link these packets. Hence, Tor can defend only against local network adversaries who do not have visibility over the large part of the network, but it's not resistant to traffic analysis attacks. So Tor can protect users against websites that track a user, as well as enemies that can observe only a small part of the network, such as the ISPs, but does not protect against attackers like the NSA. In addition to the lack of traffic analysis resistance, Tor has a few more other weaknesses. First of all, although the Tor relays are run in a decentralized fashion, the directory authorities are semi-centralized. This means that this is just a set of hand-coded directory authorities which collect and redistribute the view of the network and the measurement statistics. Another limitation is that Tor nodes are voluntary driven, hence suffer from the lack of economic incentive. This can lead to poor performance and even scaling problems. Another issue is the exit node liability problem. Since the exit nodes connect directly with the open web, the users running those nodes risk that their machine will be used to transmit possibly illegal network traffic, and hence might face repercussions from the authorities. So that's why NIM Technologies is building the first open source and incentivized mixed network, which provides network metadata privacy and protects users' communication against even most sophisticated traffic analysis attacks. It is a universal layer 0 foundation for network metadata protection. So let's first start with a little bit of background, what mixed networks really are. The idea of a mixed network exists already for a very long time, as the first design of a mixed network was pioneered by David Chaum in the 80s. A mixed network is a decentralized network of relays that ensures the unlinkability of the network communication by hiding the distinctive patterns of the metadata. In the traditional mixed network, the nodes are ordered in a fixed cascade, and each packet is routed via each node from the first to the last one. Similarly, as in Tor, by using multiple mixes, we distribute the trust among them, hence as long as a single mix in the cascade is honest, the anonymity is preserved. And similarly, as in Tor, the packets routed via the MixNet are onion encrypted. This ensures that the packets cannot be traced based on their binary representation. What differs MixNet from Tor and other anonymity network designs is the concept of mixing the traffic. When a mixed node routes users' traffic, the node collects a certain number of packets, holds the traffic for some amount of time, and then reorders the packets following a secret permutation before forwarding them to the next node. And we call such mixing techniques the batch and reorder technique. By doing so, MixNets protect against an adversary that can observe the entire network and perform even the end-to-end timing correlation attacks or other traffic analysis attacks. However, the early mixed network designs had several significant limitations. First, the fixed cascade topology scales poorly, and scalability is one of the key properties of anonymous communication networks, since anonymity loves company, so it is very important for the mixed network to scale well. The second limitation was that the public key encryption operations associated with onion encryption were very time-consuming. Also, using the batch and reorder mixing technique is limiting both from the perspective of anonymity and performance. The size of the batch is the size of the anonymity set offered by traditional mixnets. On the other hand, we don't know in which batch our packet will be accepted for the mixing, so the end-to-end latency of our packets cannot be predicted. On top of that, although traditional mixnets were resistant to timing attacks, it turned out that they do not protect against active attacks, in which the mixes can drop the packets or perform denial of service attacks, and also traffic confirmation attacks, in which the attacker observes both ends of the mixnet and tries to match the traffic based on distinctive patterns. And lastly, an important drawback was that the view of the network was determined by central authority. So in order to address the security issues of VPNs and Tor, and the scalability and performance limitations of traditional mixed networks, NIM is building a novel MixNet, which is scalable and can support both low and high latency traffic, and hence can support various applications and services. Our MixNet is open source and the nodes are rewarded for their honest work. So let's start first with discussing how to make the network scale better. One solution to improve it would be to run multiple cascades in parallel. However, although that would indeed allow to scale the network easily, I mean, we can add more and more cascades as needed, such solutions have an important drawback. When the cascades run independently, the traffic is partitioned into disjoint sets. So it doesn't matter how large is the overall traffic flow into the network, our anonymity is still limited by the anonymity set of a single cascade. On the other hand, we could use peer-to-peer topology, which scales, of course, very well. However, a peer-to-peer topology offers weaker anonymity than cascades because in peer-to-peer network, packets may pass by the same node but never got mixed because they're flowing in different directions. That's why NIM MixNet uses the stratified topology. In stratified topology, nodes are grouped into layers, and each node in a given layer is connected with each node in the previous and next layer. And traffic always flows in the same direction from the first to the last layer. So for example, in the network of 3 layers, each node in the first layer is connected with each node in the second layer, and each node in the second layer is connected with each node in the third layer. The packets are so routed, and each packet is routed by an independent path, so there are no more circuits like in Tor. And the path is composed by the sender by simply picking a single random node from each layer. Such network topology allows to scale the network easily. By adding more nodes in each layer, we increase the overall capacity of the network. On the other hand, the packets are sent via independent routes. Hence, the stratified topology ensures that paths interleave with each other at some point in the network, hence the entire traffic is eventually mixed together. So we avoid the problem of traffic partitioning. In order to improve the performance of onion encryption, we use the Sphinx cryptographic packet format. Such packet format is, for example, used by the Lightning Network. Sphinx ensures that all the packets are constant length, hence cannot be correlated based on their binary representation, and are resistant to tagging or replay attacks. In addition to those features, Sphinx ensures that the intermediate nodes forwarding the packets learn nothing about the other nodes involved in the path, except their immediate predecessor and successor. And in addition to those security features, Sphinx is also compact and computationally efficient. And you can see the current timings of our last Rust implementation, which is yet to be optimized. In terms of the mixing technique, the NIM MixNet uses a variant of a so-called stop-and-go mixing technique. As I said, traditional mixed network designs use the batch and reorder technique, hence the network must work in the synchronized rounds. Whereas in the stop-and-go technique, there is no need for synchronized rounds. So how this technique works? There is no more batching of the packets. Instead, each packet is delayed by each hop for a random amount of time. This time, how long a packet should be held by a node is selected by the sender. So the sender, when picking the mixed path, also selects for each hop a random delay and hides it in the Sphinx packet. The delays are selected from the exponential distribution. We describe this distribution with parameter lambda, which gives us a feeling what is the average time a packet will spend in a mix. And we use the exponential delays as mixing technique because it has two important properties. First of all, since the sender picks the delays, he can estimate the end-to-end latency of his packets. More importantly, the use of exponential distribution ensures a larger anonymity set. This is due to the fact that the exponential distribution has the so-called memoryless property. This property ensures that the probability that a packet leaves a mix at a certain time is independent of its arrival time. So the adversary cannot link the incoming and outgoing packets. And more importantly, the anonymity set is not anymore limited by the size of the batch, because each packet entering the mix at any point in time contributes to the anonymity set. So you're not anonymous just among a smaller group of other packets, but among all the packets which ever entered the network. Additionally to that, we can tune up and down the parameter of the exponential distribution, and hence we can support both low latency communication and high latency communication. So far we discussed the network topology, the onion encryption scheme, and the mixing technique. But what if the adversary can observe the end links of the mixed network, meaning he can see the packets flowing in and out of the network? If he sees a sudden burst of packets sent by Alice and a sudden burst of packets received by Bob, he will be able to figure out that Alice and Bob are communicating. Hence, in order to obfuscate the sending patterns of its users, NIM introduces the covert traffic. In particular, we use a special type of covert traffic called loop covert traffic. Such loop covert traffic is generated by the client and routed via the MixNet back to this client. Importantly, such covert traffic is indistinguishable from a real traffic. And we send it following the Poisson process, which means that the adversary observing the client's activity cannot infer which packets are real packets and which are loop cover packets. Hence, we give you the so-called unobservability, meaning that the adversary cannot tell when you're actually active and when not. Hence, thanks to the loop cover traffic, we obfuscate the sending patterns of the clients. But actually, we also obfuscate the receiving patterns of the clients, since the packet arriving at the client can either be some real traffic from someone else or his own loop packet. In addition to the obfuscation of activity patterns, the loop cover traffic allows also to detect malicious nodes performing active attacks, like, for example, dropping of the packets. We can further use this to measure the quality of service of the nodes and penalize malicious ones, while reward the honest ones. We call this mechanism proof of mixing, but I will introduce it in detail in future talks. So just to summarize the key takeaways about the NIM MixNet. The NIM MixNet is an open source, decentralized mixed network supporting various applications, from messaging to cryptocurrencies to decentralized apps, etc., etc. The network is fully decentralized, including the PKI, which is stored in a blockchain. NIM MixNet ensures protection of both IP and metadata, even against traffic analysis techniques, so it gives you much better anonymity than Tor or VPNs. There is no problem of logging, since the only information an intermediate node can store is from whom he received the packet and where he forwarded, but nothing more. Also, there is no fear of running an exit node, since the exit nodes do not connect directly into the open web, but to the service provider, so they cannot be penalized by the authorities. Finally, the NIM MixNet is permissionless, and the mixed nodes are rewarded for their honest work. So we have our testnet running, where as of today we have around 30 nodes. If you would like to run your own node, please visit our website or the documentation site in which we explain in detail how to spin it. Also, our codebase is open source, so please feel free to take a look. And thanks a lot for joining this talk, and I'm happy to answer any questions.
Okay, we are back live. It's a real pleasure to hear such a interesting talk that covers a lot of ground. There's so many people in the Hope community that are familiar with Tor, or at least are using Tor, and yet clearly Tor is not the answer. Would you like to comment on that a little bit, Anya, and talk just summarize sort of where you see people making choices about what anonymizer to use, and maybe in practice as well as future research?
Yes, I think I would say that Tor, without a doubt, is a great anonymous communication tool. But I think the often misunderstanding of misconception is that Tor gives you the perfect traffic analysis resistance. It's not the case because Tor was never designed to actually do it. If you're gonna look in the Tor white paper, which was published a few years ago, you will see that they actually very clearly state that Tor doesn't aim to solve the end-to-end correlation problem and the traffic analysis problems. So Tor is great, but if you would like to be anonymous in the presence of very powerful adversaries like the NSA, then you need something more powerful, like, for example, the MIX network. Of course, the MIX network which we're building is both for low and high latency communication, but I'm pretty sure some people listening today to the talk might still have this question whether like MixNets right now can replace Tor. I would say no. Mixed networks are for various applications, decentralized apps, messaging, cryptocurrencies, and so on, but they wouldn't be still the best choice for browsing the website, but this is still like work in progress. So I think Tor and Mix network, they can actually exist together in parallel.
Thank you. Thank you. That's a very clear explanation. One of the questions that came in on the chat is that they were interested to hear about the loop cover traffic description, but a basic question I think is, maybe you want to say a little more, but a basic question is whether the loop cover traffic is generated at the node or on the clients.
The answer is at both. So both the clients generate the loop cover traffic and the nodes generate the loop cover traffic. The loop cover traffic, as I described, it's almost like you're sending a packet to yourself. This sending happens following the Poisson process. The best way to intuitively think about that is that it means that the way you're sending this loop cover traffic is very natural. It's not that, for example, every 2 minutes you're gonna send a loop cover traffic or every 30 seconds. No, you rather send a certain average number of loop cover traffic within some time unit. So for example, you send 10 per minute, or you send 20 per minute, and so on. And similarly, the nodes send both the nodes and the clients. And we do that because the loop cover traffic, on top of what I said of giving you this obfuscation of your sending and receiving pattern, then actually allow you to detect some active attacks. So for example, imagine that you as a node or as a client, you're under attack in which the adversary is trying to block the traffic coming to you. Because you're sending such loop cover traffic to yourself, you can very easily detect this type of attack, because suddenly you will notice that you're not receiving back your loops, right? So you can realize that either there's something wrong going in the network or someone is targeting you. Without the loop cover traffic, you cannot detect that because you never know whether someone wants to send you a message or not. So in order to protect both the clients and the nodes, they both are sending independently their own loop cover traffic.
Okay, I think that was clear. Thank you. There's a question that I think might be related. It was a little bit of a detailed question, but it was about denial of service. It was about denial of service or distributed denial of service. And the question is, if the client is defining the amount of time or other characteristics, then could it be that the client could perform denial of service by overloading the servers in the network?
So one way to stop this type of attacks and in general the civil attacks is that the way the NIM MixNet will be functioning is that this is something what I was not covering in the talk because it's much more technical details to add. But if you want to use the NIM MixNet, you have to have a credential, an anonymous credential, which allows you to use it. This is a little bit like your monthly subscription to use VPN. So because you have this, subscription to which allows you to use the mixed network. This stops a little bit the malicious users to try to perform this type of, spamming or denial of service, attacking the network by just sending huge volumes of the traffic. So although we are allowing for this covert traffic to happen, we also have the mechanism which can, prevent the Sybil attacks and this denial of service from the clients flooding the network, just to stop.
Okay, yeah, thank you. So we had a question about incentives. We actually had two separate questions. Someone was really asking what was the incentive to run a node, whether it's an exit node or just a node in the network, and even what sort of rewards might be built in, what sort of incentives to participate.
Yeah, so in terms of the incentives, whoever wants to run a mixed node needs to stake in the network, and this stake will be the base for our incentives. So because the mixed nodes can stake, they can either get penalized if they're behaving in a malicious way and then their stake is being slashed, or they can be rewarded if they act honestly. And now in terms of the rewards, what we do is this so-called proof of mixing. So what we do, we have a mechanism which checks that if you declare that you're running a node which can support this particular volume of traffic, we expect you that you're going to do your best to meet those requirements. And we check whether the nodes actually are delivering the service which they're promising to deliver. And based on that, we're gonna share the rewards. And of course, the rewards will be proportional to the stake in the network. And in terms of the proof of mixing, how we do it, we actually use the loop covered traffic for that, and we combine it with the VRF, so the verifiable random functions. And what we do, we send from time to time, both the clients can do it and the nodes again, something what you can think about like a trap message. So it's like a packet which is generated using the VRF, and then we're gonna check whether the mixed nodes processed correctly those packets. If they did, then it means they act honestly. If they didn't, then this means they're trying to be malicious, and we have, a good argument to, for example, penalize them by slashing their stake.
Yeah, spotting that those bad actors is obviously a key feature. Yeah.
Exactly, and the rewards are distributed in the network, according to how much someone staked. But of course, it doesn't matter whether you're running an exit node or a middle node or the node in the first layer.
Mm-hmm. Someone was asking, there's a lot of interest in the loop cover traffic, as you can tell, and someone was asking in the chat a question saying that the traffic through the nodes is going to be ordered. I think you mentioned that. And how does that fit with the loop cover traffic looping back to the source? So I think they were looking at the stresses between ordered traffic and unordered traffic.
I'm not sure what the person meant by ordered, so maybe I'll repeat this thing. So the traffic is flowing from the first layer, second, third, and so on and so on. So as many layers you have, the traffic is flowing through all those layers. Now, if the client is injecting the loop cover traffic, it's very easy. It's like a normal packet, so it's going to go through all the layers. In terms of the node, of course, this has to be done in a way which cannot be, distinguished from how the other packets are behaving. So if a mixed node in the middle layer is sending a packet, a loop cover packet, then obviously he's gonna send to the next layer, right? And this packet will have to go in this same ordering of the layers. So if, for example, a mix at layer 2 is sending a loop packet, then he's gonna send to layer 3, and the layer 3 to the next one and next one. Now, it's very easy to spot that there would be a small problem with the last layer, right? If you would have the mix in the last layer, sending the packet immediately to the mix in the first layer. Here, probably the mix would be able to realize that, wait a second, I'm receiving now a packet from the last layer, but not from the client. So there is something wrong going on. And that's why we add for our mix network the so-called gateways, which facilitate they act like the entry points into the mix network, and the like exit nodes from the mix network. So before the first mix, before the mix in the first layer will receive a packet, this packet will go through the gateway. So now when a client wants to send a packet, it's going to be client, gateway, the first layer. And the same will be in terms of the packets exiting the mix network. So they're going to go last layer, gateway, and some service provider. So now, thanks to that, even if the mix in, let's say, the last layer will send the loop cover traffic, he's going to give it to the gateway, and the gateway can pass it to the first layer mix. So there's no problem that the mix node somehow will be able to distinguish that this loop packet belongs to a client or to a node.
That makes a lot of sense. So the ordering is really handled very well by the whole network.
Yeah.
Someone was curious about the ability to use NIM on mobile devices. They were sort of focused on battery use and data traffic, as we know, can get very expensive. Is this viable, do you think?
Yes, I think this is an excellent question. I don't have a precise answer for that question because this is actually something what I am very interested to measure and to see. Of course, we have to send some, because of this cover traffic, some constant amount of traffic into the network. However, our phones, when we don't use them, a lot of apps which we have still, even when we don't use them, they try to connect to, for example, keep up to date with what's going on. They have to connect with the service provider and so on. So I think I wouldn't say that right now I can promise that NIM will be for sure good for the mobile clients, but this is something what we'll be definitely investigating and checking whether it is possible to have a NIM client on the mobile phone. Because I think a question about the battery life is a very fair question, but this is something what we have to measure once we have everything running in place.
Thank you. Thank you. A question that is a little bit related. It's not about energy use, but it's about traffic. The question is about how does the overhead of loop cover traffic that you've been describing compare to the overhead of, for example, an I2P node where each client is also a relay? So I think it's maybe looking for a comparison rather than an absolute of traffic.
I mean, the comparison between I2P and MixNet, these are a bit different designs. In terms of, I see this question, overhead of loop cover traffic, I'm not sure I really understand what the question meant with the overhead of the I2P node. So I suggest the person who asked that question, if they can drop me an email and clarify a little bit what they meant, then probably I'll be able to answer this question, because now I don't understand it fully.
I think part of it was really just comparing the extra inefficiency, I guess, of loop cover versus other methods.
Yeah, I mean, the cover traffic definitely, adds a little bit of overhead. However, one very important property of the mixed network which we are using, and also the reason why we decided to use the continuous time mixes and this, cover traffic managed by the Poisson process, is that once the network grows and there are more real users who send more real messages, what happens, you can tune down the amount of cover traffic you're using, because the volume of the traffic going into the network is already so big that your anonymity is very good. We start with the cover traffic, to increase the volume of traffic going into the network, just to make sure that the anonymity will be good. If there will be a lot of users using the mixed network, you can tune it up and down depending what the requirements for your applications are.
Yeah, actually, that's I think a really good point. So what I think, if I understand, what you're really saying is that the overhead really depends on how busy the network is, because if the network is busier, then there's less overhead for the
Exactly. The previous mixed network designs very often assume that you have a constant volume of cover traffic which you have to send to make sure that your mixed network really gives you anonymity. At them, it's a bit different. When the number of users using the mixed network is small, then obviously we need a lot of cover traffic to keep up the volume and make sure that the anonymity will be good. But once there are more and more users joining and more real traffic going into the network, then you can just reduce the amount of cover traffic, so you're going to reduce the overhead caused by that.
Great. Yeah, thank you. So let's switch a little bit. We had some questions concerning things, I think they're basically related to things concerning collusion and also concerning bad actors, even at a single node level. And so the question I'll read here is, who ultimately handles the stake distribution in the network? So if a node is dishonest, or if two nodes are colluding, that type of thing, then who is responsible, or how is node reputation then handled, and how, and I think a related question, I'm sorry I'm giving a few points here, but I think a related question is, if clients are able to report potential misuse, how do you know to trust the clients, because they might be lying?
Yes, so what happens is that's also one reason why we use the VRF to generate the loop packets, which are gonna be used to check the honesty of the mix nodes. By using the VRF to generate those loop packets, we ensure that the clients, they cannot try to frame the mix nodes. So both the client can prove that he sent actually a loop message to check the honesty of the mix nodes, but he cannot forge that packet later in time, right? So this is handled by the VRF. So this ensures that the honest clients can prove if the mix nodes are dishonest, but dishonest clients cannot frame honest mix nodes. And in terms of the question of the stake distribution and who gets notified of that, that's why we use a blockchain. So what happens is that the mix nodes, they will have to, from time to time, publish to the clients, to all the users of the network, some information about what packets they observe flowing through them. And this information can be then verified by the clients. So the clients can see whether the measurement loop packets which they sent were really processed by those mix nodes. And if not, then they can raise an alarm, and we have the validators for handling the blockchain. And if the client sees that, oh, my loop packets which I sent to check the honesty of the mix nodes were not included in the information published on the blockchain by the mix nodes, then I can come to the validators and make a complaint about the nodes.
Is there research on the relative quantity of things like collusion or bad actors in, I guess not so much in the NIM, maybe there is on the NIM network, but I think in the Tor network. In other words, we know that state level actors are a big concern that we want to protect against, but we know that there are more, maybe innocuous or generic, like the script kiddie equivalent of bad actors. So do we know how much that goes on?
I mean, you mean like how many clients can be malicious to make sure that the network will be still okay, or how many nodes can be malicious?
Well, that's actually probably a better thing to talk about, because it's more on the technical side. I think I was more curious from your research, the extent to which bad actors are present in real networks. In other words,
To be honest, right now we didn't take such measurements, to see how many actually in the networks can be bad actors. This is for the future work. What we've been rather simulating at NIM is how many nodes can be, how many nodes can be malicious in our network, and yet we still can ensure the anonymity. So here you're looking at two separate topics. One topic is malicious nodes who perform active attacks, so who, for example, drop the packets. The other question is the silent malicious nodes, so the nodes which don't perform any active attacks, but they just sit and observe the traffic flowing. And the question, when you have the active malicious nodes, the proof of mixing will detect them. But the more tricky question is, what if you have the silent nodes which just look at the traffic, they don't perform any active attacks, but they would like to try to trace the client. So what we've been doing, we've been simulating a little bit the second behavior, looking like, what if 50% of mix nodes is malicious? What if 80% of mix nodes is malicious? Is our network still safe? But looking at how many actually nodes are malicious in like real deployed network, we didn't do it yet.
Could you tell us a little bit more about the test network, or the, if you have a code base or something like this to do this testing and simulation, and how scalable it is?
So the simulation for like testing of the, passive nodes which try to like trace the packets, this is done internally. We have like a simulator for the Mix network, and for now we just do those simulations internally. In terms of the testnet, there's obviously a testnet running. If anyone wants to run a node, they can do it. We didn't try, any analysis in terms of attacks on our testnet, just the internal one, the simulator. And the simulator, what simply does is it mimics the behavior of the actual mixed network, which will be running in the future. So then we can always say, we would like to simulate this many malicious nodes and see, for example, how often it happens that when you pick a random path, it's a fully malicious path. So all the nodes are malicious, right? And we look how often this happens given various percentage of the malicious nodes.
Thank you. Yeah, this has been a fantastic discussion, and I appreciate the presentation, the pre-recorded part, and also all these questions. And thank you to the audience. We have some fantastic questions happening in the Matrix chat, and I hope I'm doing an okay job of conveying them to you. Later, we'll get more sophisticated in the program, and we might invite some questions into the Zoom, but we're still warming up on that level of sophistication. So I think the only other thing I want to make sure you do is mention a website or email or anything else, or papers, anything else where people would go to get further information about this.
Yes, if you would like to visit our website, it's nimtech.net. And on the website, you'll find links to our Telegram room. You're going to find links to the documentation, which can help you if you would like to spin a mix node on your own. You can find a link to our open source code base. So everything is on the website. We also have the Medium account in which from time to time we post some blogs. So if you want to take even more in-depth look into how the MixNet is working and so on. So I'd invite you to do it. And of course, if you have any questions, just feel free to send me an email or to ask me on Telegram, and I'm more than happy to answer all your questions.
Thank you. Well, thanks for being with us. Thank you for submitting your talk to HOPE. I know the audience has enjoyed it. I've been speaking with Anya Petroska, who is someone who had done her PhD in anonymous communication systems at University College London. And as I think we've been hearing for a while now, is focused on resistance to NSA level global adversaries with the NIM MixNet. It's been a true pleasure. Thank you for being with us, and we'll start again.
Thank you so much for having me, and thanks for the great questions to the audience.
It's been a pleasure, and we'll be back at the top of the hour.